At this point, if you have ever executed a real-through graph, you have already used the evaluator node. The evaluator node belongs to the category of the execution nodes. The nodes you will find in this category let you decide the way your graph is going to be displayed and executed. We have already explained some of the nodes that help you keep your graph clean and tidy. These nodes are the compound node, the input interface and output interface nodes, and the pass node. You can watch their description in the tutorial titled Making Your Graph More User-Friendly. Among the remaining nodes, some of them are designed to provide extra control over the graph performance. These nodes will be explained in a separated video, and they are Get Graph Number of Threads, Graph Purge Memory, Kernel, Memory Usage Info, Node Purge Memory, Pin Purge Memory, and Set Graph Number of Threads. Finally, the get and set global variable nodes are extensively described in the tutorial titled Sharing Data Between Graphs. Therefore, in this tutorial, we are going to see in action the following nodes in this order: message print, evaluator, selector, concentrator, sleep, graph cancel, condition if, and the for node. Let's begin with the message print node. The message print node is arguably the most used node type, only second to the evaluator. It displays on the messages panel a text representation of the data connected to its input. Additionally, the output of the node is a pass-through of the input connection. This way you can insert your message print node wherever it is necessary without increasing the cluttering of your graph. When the input data of the message print node is not of the string type, it either displays a default text or a message saying that that type representation is unknown. More specifically, the message printed is preceded by the node name, the colon character, and a white space. Let's see an example when trying to print some string data. We just create a string constant node, and then we can type some value. After executing that, the exact message is message print 01, hello. Now let's write with a non-string type. For example, the integer type. We create an integer constant and again type some random value. Let's connect it to the message print and execute the graph one more time. In this occasion, the message looks exactly as expected. Well, let's finally try with a real number. I will set its value to something like 2.5. If we evaluate the graph again, the output is not as predictable as before. Yes, it is 2.5, but there are a total of 6 decimal places. 5 of them are redundant in this case. This is why I mentioned that non-string types use a default non-customizable conversion to text. Let's see what happens if the input of the message print node is an array of more than one element. First, we can simply split the string constant into every one of its characters. In order to get this, we can use the string split node. We have to leave the separator empty to get the isolated characters. We are ready to execute the graph again and see what's the output. It's important to notice that the input of the message print node is an array of 5 strings. In this case, every string is printed followed by a comma and a white space character. Let's introduce a new type in the example, the bit type. We can create an array with random bit values using the array bit random node. Let's make its size 5, like in the string example. If we print the bit array, the result is a sequence of ones and zeros. It is a very compact representation of the data contained in the array, much more compact than trying to print a sequence of true and false keywords. Now it's time to check what would happen with an array of integers. In this case, I will create a constant array for the integer value. Let's set the size to 5 and run the graph. This time, the output is exactly the same as when we printed just a single constant. The message print node only prints the first element of arrays of number types. There is a reason for this behavior. Realflow graphs are expected to work with huge amount of values, especially particles. If by mistake we print such a huge amount of information, chances are high that the messages panel will be completely flooded, but this does not mean that you cannot print your whole array of numbers. You can use the numConvert node to translate any number array into a string. The conversion to string is just one of the conversions allowed by the numConvert node. Let's see what's the output of the graph if we execute it again. There it is, the complete sequence of integer constants. At this point, you probably already guessed that the numConvert node will not let you customize the number of decimal places for your real number. This is why we have the real to string node. It features two inputs, and the second one is exactly that, the total number of decimals that will be displayed. Let's clamp it to 1 and test this last example. It's right what we wanted to see from the beginning. While we create some extra string converters for you in upcoming updates, feel free to design your very own ones using the existing string operation nodes. If you are happy with your creations, you can export them as compounds to be reused and shared everywhere. Now it's time to explain everything that needs to be known about the evaluator node. The evaluator is the most important node in Realflow graphs, and because of that, it features its own special shape. Evaluator nodes are terminal nodes. The main purpose of the evaluator is to decide which branches of a graph will be evaluated or ignored. The evaluation of a graph can be described as follows. The graph finds all its evaluators. Then, for every evaluator, every node and pin that is connected directly or through several connections to the evaluator is flagged as necessary to be evaluated. We can also call this state, not up to date. In the next step, for every evaluator, its pins are computed from top to bottom. Evaluating an input means that, if it is not up to date, it asks the node connected to it to compute its related output value. In order to compute this value, most nodes will need to make sure that their own inputs are also up to date. Therefore, an evaluator pin triggers the recursive evaluation of the nodes it depends on. Most nodes' computation process begins with the update of its inputs. That way, the user feels at the end of the execution that the nodes have been processed from left to right. However, as we have seen, the evaluator is actually recursive. For this reason, a node execution does not stop until all its dependencies have been resolved. This is why, when you right-click on a pin and check its execution time, the value displayed is usually bigger the closer it is to the evaluator. It is important to mention that, right now, it is not possible to decide the order of execution of the evaluators in your graph. Off the record, all we can say is that their order of evaluation is the same as the order of creation. But this cannot be predicted if the graph is loaded from disk or pasted from somewhere else. To have total control of the order of execution, you need to create several pins in a single evaluator. Of course, you can create, rename, and remove evaluator pins. And it is also possible to merge several evaluator nodes into a single one. One more way of controlling the order of evaluation is using the concentrator node. This node is explained later in this very same tutorial. One last restriction about evaluator nodes is that they can be created only at the root level. The execution of a graph triggers the evaluation of all the evaluator nodes. However, it is also possible to evaluate just a single evaluator or an evaluator pin using the right-click menu. Before moving to the next topic, I would like to show you the importance of one of the buttons of the top toolbar, the Press and Hold to Highlight Nodes that will be evaluated button. Its name is pretty self-explanatory. When you click and hold that button, only the nodes from the graph that will be actually evaluated remain active. The rest of the nodes and pins look disabled, like when you are trying to connect something to them but it is not compatible. For a simple graph like those we have tested so far, it's not such a big deal. However, when your graph starts getting more complex, it is always nice to check that everything is connected as expected. If something is wrong in your graph execution, I would recommend you to press this button as your first choice. It might save you a lot of time spent trying to find a missing connection in your whole graph. Now, let's see what's the point of the selector node. In a few words, the selector node is like a pass-through node, but with complete freedom to create input and output pins and choose the connections between them. In fact, a selector node looks and acts exactly like a pass-through node when it is created. Once you add its first extra input or output pin, it begins to make more sense. The selector node allows the creation of internal connections between all its input and output pins. This way it's possible to switch different branches of the graph without modifying the connection layout of the graph. The selector is completely user-driven, and it cannot be modified at graph execution time. Let me create a simple example using the selector node. I will create a graph to be able to switch easily between the display of particle positions and object vertex locations and real wave mesh vertices. First, we add the necessary nodes to compute the particle positions. These are basically the get particles and particle get channel nodes. Okay, now we can create the nodes to get the object vertex positions. We are going to display the vertex of real-flow objects, so first we will create a get object mesh node. Then we need to get the object vertices. Once we already have the object vertices, we can query their positions. That's what the vertex get channel node is for. Now we have the positions of both the particles and the vertices. The positions of real wave vertices are computed the same way as those of the object. Let's duplicate that part and add the get real wave mesh node. We will only display one of them at a time, so we need just a single DisplayPoint3 node. Increasing the size parameter will help us see the result in the viewport. We can already connect it to an evaluator. In this case, we have 3 branches and we want to connect them to a single input. This is when adding the selector comes in handy. Let's create a couple of additional input pins for the selector so we can have one for each of the branches. The output of the selector is going to be the array of points. We can connect the particles to the first input, the object vertices to the second, and real wave vertices to the last one. By default, the selector already connects the first input to the first output. Let's press the button that highlights the parts of the graph that are going to be evaluated. As you can see, only the input internally connected to the output is taken into account. The other 2 branches are completely ignored. Before testing the graph, let's add an emitter, an object, and a new real wave to have something to work with. I'll give the emitter an initial volume to create some particles. Let's also add some interesting wave to the real wave. Okay, now we can select the emitter and the object in the graph. We are ready to execute the graph and check if the result looks as expected. There we have it. Only the particle positions are highlighted. Now we can play with the different combinations in the selector node. We can switch to the display of the object vertices. Let's see it. There it is. We can finally show the real wave points as well. Everything does what it's supposed to do. If an output of the selector node is going to be evaluated, make sure that some of the input is connected to it. Otherwise, it will result in a warning message and no actual value will be provided to the output. Let's disconnect the real wave vertices and run the graph again. We can see the warning saying that there is nothing being passed through in this case. A selector can have as many inputs and outputs as you wish. Let's add an extra DisplayPoint3 node and paint dots with different color. Then we can create one more output for the selector node and connect it to the new DisplayPoint3 node. Now we are free to test any combination of inputs and outputs to display the data in different colors. This way we can modify the graph behavior without having to change any of the connections between graph nodes. All we have to do is modify the internal connections of a single node. If you want to decide which branch of the graph is executed in runtime, it is necessary to use the condition if node. Later, In this very same tutorial, I will explain how to work with that node. I would like to talk now about the concentrator node. The concentrator node looks exactly like the selector node. The user interaction with that node is also the same as with the selector. However, its purpose is completely different. The concentrator node can have many inputs and outputs, but its execution always follows the same pattern. Whenever any of its outputs needs to be updated, all the concentrator inputs are evaluated from top to bottom. Internal connections are allowed for the user to decide which data from the input pins needs to be passed through. The most common way to use the concentrator node is when you don't want to propagate some data any further in the graph. So, in that case, you will want to have more inputs than outputs. The best example of this is when you have a compound that performs several tasks, but you only need one particular data to be exposed outside. First, I'd like to demonstrate that the order in which the outputs of the concentrator are requested does not affect the order of evaluation of its inputs. For this test, I will simply add 3 message print nodes and a concentrator with 2 outputs. Then, I will let the concentrator pass the first and second message print nodes. I will simply connect both concentrator outputs to a new evaluator. Now, if I execute this graph, we can see the output message order. It is just 1, 2, 3. If we press and hold the button to highlight the nodes that are evaluated, we can see that all of them are. It is being so even while the third message print node is not propagated anymore through the graph. Let's see now what happens if I switch the order of the 2 outputs. I'll execute the graph again. The messages order is exactly the same as before, even while the message print 2 output is passed through to the first input of the evaluator. Let me insist one more time. Concentrator nodes always evaluate all its inputs and they do it from top to bottom. Now, I will open one of the demo scenes to avoid recreating a scene from scratch. Let's use the scene called Stat Spectrum Preview. This example displays an ocean statistical spectrum image in RealFlow viewport applied to a plane. We can create a compound for this whole scene. If I execute the graph, everything should, of course, behave exactly as before. Let's get inside the compound and find a place for a new concentrator node. I will add it right before the output compound interface. Now, we can create an additional input pin on the concentrator to make some extra stuff inside the compound. We can begin by adding a wireframe visualization of the output mesh. It is as simple as adding a new display mesh node. Let's make sure it is set to display the wireframe and the color is different. Let's execute the graph and see what happens. And as you can see, the wireframe is there. If we press and hold the button to highlight the nodes that are going to be evaluated, we can see that the branch that displays the wireframe is highlighted too. So, to sum things up, the concentrator node lets you evaluate branches of the graph without the need of finding a terminal node for them. Now, I will show you a very simple node, the sleep node. The sleep node freezes the execution of a graph during the time specified by the user. As the parameter name suggests, the time is given in milliseconds. Making an example of the sleep node is really easy. Let's just create a sleep node and connect it to an evaluator. Then, if we execute the graph, we can see in the messages window how long did it take. Since the sleep time is set to 0, the graph execution takes a very short amount of time. Let's simply change the sleep time to 1 second, or in this case, 1000 milliseconds. And now, the graph took 1 more second to be evaluated. After this brief explanation of the sleep node, let's see the graph cancel node. The graph cancel node makes it possible to stop the execution of the whole graph at any location. When you create the graph cancel node, you find 2-bit inputs besides the usual input and output pass-throughs. The graph cancel node evaluates first its cancel input value. If it is false, the execution continues just like if the node were a simple pass-through. However, if it is true, the execution of the graph is aborted and the input pin of the node is not evaluated. Additionally, if the quiet input is false, an error message is displayed both in the node and in the RealFlow messages dialog. Let's see the graph cancel node in action. In fact, I'm going to use again the Stat Spectrum Preview demo scene. In this case, I will update the waves only during the first 20 frames. For the rest of the simulation, it won't be updated anymore. So I can place, for example, the graph cancel node right before the display mesh node. Later, we have to do the most important thing, compute the cancel condition. We can already access the current frame number thanks to the getCurrentTime node. Since we want to cancel the graph when the frame number is bigger than 20, I will create a condition filter by creatorRun node. I just need to add the integer 20 constant. The Boolean mask of the comparison is what we are going to connect to the cancel input of the graph cancel node. For the moment, I don't want to display any error, so I will set the quiet parameter of the graph cancel node to yes. So now, it's time to reset the scene and check if it works. It works. For the first 20 frames, the wave was animated. However, after that point, the simulation became much faster and all we could see was the last computed state of the ocean statistical spectrum. We can swap the quiet parameter of the graph cancel node. This will make RealFlow display a lot of error messages after frame number 20. Let's see it in action. And there you go. The errors are on the messages window, and you can also see it in the graph which node cancelled the execution. Now that we know how the graph cancel node works, we can go a bit further using the condition if node. The condition if is a very powerful node located inside the condition category. With this node, it is possible to switch between different branches of the graph at execution time. It has 3 inputs and 1 output. The first input is the Boolean condition that decides which one of the 2 inputs is actually evaluated. Below, there are 2 inputs. The true value is the input that will be passed through the output in case the condition is evaluated to true. Therefore, the false value input will be passed through the output when the condition is false. It is really important to make sure that both types are compatible with the output, otherwise, RealFlow might even crash when trying to perform an implicit conversion between the types. Let's reuse part of the previous example to show how the condition if node works. Instead of doing nothing, let's display a different mesh when the frame number is bigger than 20. First, let's swap the graph cancel node with a new condition if. Since we want the wave to be displayed for the first 20 frames, we must connect it to the false value input. We can connect any other mesh to the true value input. Let's just connect a mesh cube node. And that's all. We can reset and simulate. In this case, after 20 frames, the wave has been replaced by a unitary cube. I'd like to explain one more thing about the condition if node. When you press and hold the button to highlight the nodes that are going to be evaluated, both input branches of the graph are highlighted. This is because the value of the execution can change at runtime, so any of the branches could be actually evaluated. We have reached the last topic of the tutorial, the for node. You can find examples of the usage of the for node in some of the previous tutorials, like in the tutorial about arrays. There is also a longer explanation about compounds in the tutorials titled Making Your Graphs More User-Friendly. The first thing you need to know about the for node is that, as an iterator, it needs to be inside a compound. It cannot be at root level. This is because the compound where the for node belongs to is considered its scope. Let's see a visual example about what really happens during the execution of a for loop in a RealFlow graph. In this diagram, we have a compound with 2 outputs connected to an evaluator. There is a for node inside the compound. This fact will affect the way the nodes inside the compound are evaluated. The execution of the graph begins as usually. For every evaluator, all the nodes and pins that end up linked to it are set as not up to date. When the evaluation reaches the first compound interface node, the compound iteration process begins. Since the compound contains an iterator, the first step is updating all the necessary inputs of the compound. The next step is finding all the output interfaces that are going to be evaluated in the whole graph, not just the one that triggered the compound evaluation, all of them. Then, all the nodes and pins inside the compound that end on these output interfaces are set as not up to date. Since this is the first iteration, there is no need to do that. Now, the iterator node computes its output value. Let's say that it is a 3-iteration for loop, from 0 to 2. In that case, the output value of the for node is set to 0. Then, the output interfaces are evaluated just like a standard evaluator would do. Once the compound body is up to date, the process starts again, just as many times as the number of iterations in the loop. After the last iteration, the compound outputs are finally up to date, and the execution of the graph can continue as expected. Now that we have seen how a for loop behaves inside a graph, let's build one example using it. In this example, I will use the RealFlow icon as a template to build a two-dimensional grid of cubes in the scene. The most natural way to walk through an image pixels is using a nested loop, one loop for visiting the columns and another loop for the rows. Let's start by creating a new graph in the Simulation Press stage of the Simulation Flow window. The first thing we need to do is loading the image that we will use as a reference. It is as simple as creating an image load node and setting its input path. As I said, it's going to be a small RealFlow icon. We need basically two things about the image: its size and its pixel colors. The size of an image is available through the image info node. And the colors of the image can be retrieved with the getImagePixels node. Now, our intention is to access every pixel of the image to create a new RealFlow cube. So, at this point, we already need to start traversing the columns or the rows of the image. Let's create an empty compound and call it rows. For this compound, I will create the three necessary inputs. Two inputs for the width and the height of the image, and one more input for the colors. A compound always needs at least one output to be evaluated, so let's create it. We can connect it to an evaluator. Alright, let's get inside the compound. At this first level, we will visit the rows of the image. Therefore, we have to create a for loop and use the height of the image as the stop parameter. The start and step parameters can be left with their default values, 0 and 1 respectively. Okay, actually there is nothing else that we want to do at row level. All the operations that we are going to perform are per pixel. So we have to create one more compound for the nested loop. Its name is going to be columns. In this case, we want to pass a total of 4 variables inside the columns compound. First, the very same 3 inputs that the parent compound has. And one more input for the current row. Again, we can create one output for the compound and connect that to the output of the current one. We can already get inside the columns compound. Let's remember what we have to do. We need to create a RealFlow cube. Then we have to move it to a position related to its pixel coordinates. That will simply create a grid of cubes. Finally, we can access the pixel color and assign that color to the new cube. So let's begin by adding the cube. We can use for that the scene add object node. In order to change the position of the cube, we can use the set transformation from components node. We can set its scale to something close to 1. And for the translation, we can create a new vector3 value according to its components. The X component will be the row. And the Y component is the current column. This is enough for the transformation of the cube, so let's change the color. We already have the pixel coordinates and the whole array of colors. With the getArrayNum to the element, we can access the exact pixel color we want without any extra computation. And then we can modify the color of the cube using the setNode parameter node. The name of the parameter is color, so we can connect the cube and the pixel to it. So far, we have computed 2 different branches inside the compound, but we only have one output interface. Instead of creating an extra output, we can use a concentrator node. Let's connect the output of the concentrator to the output interface. And now, we can create one more input in the concentrator and connect both branches. If everything is okay, we have almost finished. I will add an extra graph right before the one we just composed. In this new graph, I will remove all the existing objects in the scene. This way, every time the simulation restarts, the older cubes are removed from the scene right before adding new ones. Well, let's limit the number of frames to 1 and see if everything works as expected. There it is. The RealFlow logo is there, but it appears upside down. That's because of the order in which the pixels of the image are read. If you wanted to fix that, it would be as simple as inverting the row number when searching for the color of the pixel. But the main point is that the nested for loops work. And now we have the RealFlow icon represented with colorful cubes. That's all for this tutorial. Thanks.